Alright everyone, so here we have at a construction site a 22 kilogram bucket of concrete is connected over a frictionless pulley to a 375 Newton box on the roof of a building. There's no friction on the box since it's on wheels, essentially. If it starts from rest, we want to draw free body diagrams of the bucket and the box. We want to find the acceleration and how fast it's moving after the bucket has fallen 1.5 meters. So if we draw the free body diagram for the block on the roof, we see that we have the force of gravity that points downwards, the normal force that points upwards, and the tension in the string that pulls along the direction of the string. For the bucket hanging off the roof, we have the tension in the string and the force of gravity pulling downwards on it. So these are our free body diagrams. These are all the forces acting on these two objects. So one way to think about this is to think about two objects in a straight line with one another. The object on the right is the bucket. It's going to be the thing that's pulling. And the object on the left is the one that's on the roof, and it's going to be the thing that's kind of pulling back on it, slowing it down just a little bit. So we can draw the force of gravity and imagine it moving forward with the tension pulling in the opposite direction. In this case, we can take downwards to be positive. And we can see that the tension on the block on the roof is in the same direction as the force of gravity on the bucket hanging from the roof. And because these two cords are connected, these two tensions are equal to one another. The normal force and the force of gravity cancel each other out and act in opposite directions from the motion. So we don't have to consider those when we're dealing with these equations. So using Newton's second law, the sum of the forces on the first mass, the one on the roof, which is just the tension, is going to be equal to the mass times its acceleration. In the same way, we can write an equation for the mass hanging from the roof. And then we have the downward force of gravity and the upward force of tension. Remember, in this case, we're going to take downwards to be positive. So that means that if we draw on this picture, positive x direction is to the right, which means the force of gravity is positive and the tension is negative. So now we have two equations, and what we're looking for is the acceleration. Now we know that the tension is equal to the first mass times the acceleration from the first equation, so we can just plug that in. And now to find the acceleration, we just need to solve for a. Just moving that m1a over to the other side of the previous equation, we can then factor out a. And then solve. You find that the acceleration is equal to the mass of the bucket hanging from the roof times g divided by the total mass of both objects together. And we plug all the numbers in. Now here we just need to go back and calculate the mass of the first block. Well, the weight is given us 375 newtons. For some reason, when I did this, I did 350 newtons. The idea is still the same. So, if I had used the appropriate weight from the problem and not miswritten it as 350 newtons, you would have gotten 38.27 kilograms, which would have adjusted the final answer here. But the idea is still the same. You would just replace this with 375, not 350. Finally, for the last part, we're just going to use kinematics. Now that we know the acceleration and we know the distance that it travels, we know that it starts from rest, we can determine how fast it's going. So using the third kinematic equation, And so here you would find the final velocity is 3.35 meters per second.